Okay, let's get started. Welcome back. I hope everybody is staying safe and staying home. Today we're going to kind of pick up where we left off last time. And while this is non-optimal, I think that we're going to get through the rest of the semester. Everything will be just fine. But we'll figure it out as we go. All right, the first thing is the way I'm going to try to do these lectures, at least initially, is I'm going to record them. They'll be on YouTube, so you can watch them from a mobile device or wherever you want to. And then what will happen is you can watch those, post questions in the comments section, or message me directly. My cell phone number is on the course syllabus, so feel free to look at that and send me a text message or even give a call if you need to talk through something. But for this presentation, go and ask the questions in the comments section or send them by email to my email address. Okay, let's get started today. Today we're going to talk about error correction. And if you remember what we did last time we had talked about the error kind of detection methods. And so error detection methods, looking at a few of those, let me adjust the volume just slightly. Looks like we're overshooting that. Okay, it looks a little better. Okay, so last time we talked about error detection. And with error detection, we had basically what we're concerned with is knowing if something went wrong or knowing if there was an error. And there were several methods that we looked at for determining that. Parity, in other words, just looking at the pattern of bits and deciding whether to add a bit or take a bit away. In other words, whether the added bit is a 0 or 1 to make it either even or odd. Block parity, which does the same thing, but does it over kind of both the horizontal and vertical direction of the block of data. Arithmetic checksums, you just add up all the byte values, usually mod it by some value to limit the size of it, and then that becomes a thing. And then one of the ones that's kind of like the gold standard that's used all over the place is cyclic redundancy checks, because they are very similar to an arithmetic checksum in that we're taking all of the data, kind of summarizing it, but we're doing it as this kind of modulo 2 long division that we looked at last time, now over a week ago when we met. But the CRC has this benefit that it's very hard to have offsetting errors in it, so it's a very effective, but still very easy to calculate because we just have to cycle through all the bits, performing that XOR on that or shifting. So really on a microprocessor it's easy to implement, but it's highly effective, much more so than any of the other ones. Now those are good for detecting errors, but what do we do if we don't just want to detect that they happen? What if we want to correct them when they do happen? In other words, we want to receive the message and then be able to fix the problem as it occurs. So the idea there is that method 1 is kind of using error detection that we already know how to do. And this is called ARQ, or automatic repeat request. And the idea behind ARQ, error correction, is that we detect the error when it happens. We then tell the sender, hey, that thing was bad, there's an error in that. And then the sender then resends or repeats the previous thing that was said. In other words, it's like in a conversation when you didn't quite hear what somebody said and you say, excuse me, I didn't hear that, and then they repeat that. Now, the only thing about that is that it requires the ability to ask back to the sender to say, hey, repeat that. There has to be this kind of back channel or this duplex communication between the sender and the receiver in order to say, repeat that. Otherwise, you can't have an ARQ type error correction method. And there are a few different types of ARQ, so let's just look at a couple of those here quickly. So the first type is kind of this stop and wait. In other words, the sender sends one single frame of data. That single frame of data, when it's received, gets analyzed for error. If it is okay, then the sender says, or then the receiver says, acknowledge or yes, that's good. And then the sender sends the next one. If the single frame of data is bad, then the receiver says no or negative acknowledge, NAC, and then the sender resends the current frame that they're on. Now, the problem with that is that if you have a high latency system, then you'll be waiting a lot of time to get a response before you're going to the next frame. So something on the internet where you're sending a lot of data along a large latency or kind of signal path, then it would take a lot to get through a large amount of data because you always be sending, wait. They either say yes or no, and then we either go to the next one or resend the one we're on. But it is simple to implement, which is good. And for a low latency environment, that might be okay. But in something where you have a lot of data, where time matters, the bandwidth matters, we have these other kind of possibilities here. One is this go back N. And what go back N does is rather than sending a single frame, you send like a group of frames. Let's say you send 10 of them all at once. So you send 10 of these messages all at once, and then the acknowledge sends back the sequence number, the number of the frame of the packet up to which everything had been received correctly. So in other words, you could say, I received 10 were received. I got all of them up to 8, but 9 was messed up. I might send a negative acknowledge for 9, an acknowledge for 8, negative acknowledge for 9. And that means that I don't have to send an acknowledge for every one of the frames. And that can be very useful because you can have this kind of sliding window effect where you have this group of 10. When we acknowledge up to 8, that gives us now up to 18 we can send. So we'll always have 10 of them in the process of being acknowledged. And any acknowledge of a number means implicitly that I got all of the ones up to that one correctly. So I don't have to send a lot of traffic with acknowledge. I really could say I got all 10, acknowledge 10. Then the sliding window moves over to the next group, and now we have the next group of 10, and the next group of 10 comes in. If I miss one of those, I acknowledge up to 8. They resend 9 of that next group, and then so forth, and that window just keeps moving across the data, and that could be a really large amount of data that we're moving through. Now, the selective repeat is similar, except that we're sending all these packets, and then only the missing or damaged ones are re-requested. In other words, we have this kind of negative acknowledge that we can send, where they just keep sending packets, and then we say, oh, I missed number 5, I missed number 8, I missed number 27. And so basically just cycles through only selectively repeating certain frames up to that. Now, those two are similar in that they have multiple frames of data in process at any given time. Now, one thing to note about all of those, these are all ARQ methods, and because they're all ARQ methods, there's something that's important to keep in mind with that, and that is that with an ARQ method, we have to have a back channel, and we're also using some sort of error detection on the packets. In other words, one of the methods we saw before, probably like a CRC would be used, and if a CRC detects that there's an error, we re-request it. But to do that, perform that re-request, we have to have a duplex communication connection, and we have to have that ability to re-request whatever was damaged or missing. And that's a pretty common methodology to use. Now, ARQ then requires a few things. The first thing is obviously redundancy in the form of some error detecting code, a CRC, a checksum, even something simple like Parity could be used, but more than likely it's going to be something like a CRC. We also require duplex communication. We have to be able to re-request damaged or missing data. We need some sort of two-way communication in order to perform that re-request. We also need some sort of protocol or some sort of rules that say, how does the re-request process work? In other words, if we have that back channel, we have to know what does it mean to say good, or what does it mean to say bad? What does it mean to say acknowledge versus negative acknowledge? What's the rule set that we both agree upon for me to perform those re-requests and for them to get kind of fulfilled? So we have to have those three things in order to have an ARQ protocol or system that works. We need to have an error detecting code. We need to have a way to talk back and get information to the sender from the receiver, whether it's a positive acknowledge or negative acknowledge, and we need a rule set that says how do we deal with those messages when they come back? What's the process we're using to do that? Now, one thing that comes up, though, is what if it's impossible or inconvenient to have that communication channel back to the sender? And what would be some cases where we would have that? Cases where we would have that difficulty would be something like satellite communication. So imagine like your satellite TV, direct TV, or Sirius satellite radio, or you might even think of like kind of a digital television transmission. That's a one-way communication. Your receiver does not talk to the satellite. It just receives data from the satellite. So the question is like, well, what if that data gets kind of corrupted in some way as it's being transmitted? We don't want to lose the entire stream. We want to be able to reconstruct the message that was destroyed. Same thing with spacecraft. The distance that spacecraft, for example, you have like Voyager or some spacecraft that's out near, I don't know, Neptune or something like that. The amount of time it would take to send something and then have to receive the re-request would be like hours, or wherever Voyager is right now, we would end up with just, it's so far away, it would take so long to get that re-request message back. And then what happens if that gets lost? So the idea there is the distances, where distances are great, the latency is much higher, the cost of having to re-request data becomes much higher, and it gets worse and worse the farther away it is. And that's actually something about satellite communication as well. It takes time for the data to get up to the satellite, and then from the satellite back down, and having to perform a re-request with something that is in orbit, a geosynchronous orbit, there's this inherent time delay that just cannot be overcome. Also, things like CDs and DVDs, you have the content on there. There's no way to re-request from the CD other than read that section again, and some CD players, DVD players do overscan. They read multiple times over the same section of the disc. But at the same time, the ideal thing was you read a block of data off the CD or the DVD, you process it, it perfectly now has the audio, or in the case of a DVD, the video frame that you want. And so the idea there is we really have this kind of one-way real-time communication that we don't have time to go back and read parts again and again and again, because we have a stream of data that needs to go out to the speakers or to the screen, and we don't really want to pause things while we read the thing again. And so in that case, scratches, dust, other things are going to happen to those disks, so we need some way to do that. Also, hard drives in some sense, similar thing. Optical systems, like a QR code or IR communication with a remote control, those are one-way things. You can't, with a QR code, you can read the code, look at it, but you can't really, it has no logic in it, it has no ability to talk back to you, it's just a one-way communication of the light bouncing off of it going into a camera that's reading it. And so if part of it gets obscured or part of it is missed, we would like to reconstruct that and make sure we're not having corrupted data in some way. And so all of those things are cases where we don't really have a back channel. We can't ask again. And notice that there's some passive things like CDs, DVDs, and optical systems down there, at least the QR codes or other barcodes. IR communication systems, satellite, and spacecraft are all active systems, but it's the same kind of problem. We want to have it so when we receive the data, if it's damaged, we can fix it. So the idea is, how can we deal with that? Or how can we set up a system that does that? And the answer to that is the same as how we do error detection, and that is redundancy. But in this case, rather than just enough redundancy to tell if there's a problem, what we're going to do is we're going to add redundancy on top of redundancy on top of redundancy. So not only can we tell that there's a problem, but we can tell exactly, we can pinpoint, okay, we know that here's this block of data, we know there's a problem somewhere in it. And what if we add enough redundancy, we can say, okay, I've detected there's a problem, and here's where the problem is, now let's fix it. So what we're going to do is we're going to use the power of redundancy in a different way than we used it for error detection. We're going to use it to not just say there's something wrong with this block of data, we're going to use it to say that there's something wrong, and I know exactly where it is that's wrong, and I can fix it. So we're going to use redundancy to try to fix the errors. And that method, notice, is different than ARQ because we're not re-requesting, hey, send it again. We're saying that I received one block of this data, I can check and see if it's good, and then I can say if it's not good, I can fix it. Now, there are limitations to that we'll see here in a second, but that whole process is called rather than an error detecting code. That's an error correcting code. But notice that the two are closely related, that they're both using redundancy, just in a slightly different way. And we're going to need more redundancy for an error correcting code than we have for an error detecting code. All right, so error correcting codes, or sometimes called forward error codes or forward error correcting codes, those basically what we do is we add redundant information. We put that into the channel along with the data in some way. And then we have to have enough redundancy that allows us to reconstruct the message if errors are detected. So in other words, we can still do a quick error detection, and then we can say, hey, if there's an error, I'm going to use this redundancy to fix that error. So notice that there's no back channel required. So this is distinctly different than ARQ. So forward error correction is distinctly different than ARQ is. And notice that means it can work with simplex communication, like satellite transmission, a spacecraft at the edges of our solar system sending blocks of data back. Even if some of that data gets corrupted, we can still reconstruct the parts that were missed. All right. Now, one thing to note is not all errors can always be corrected. It depends on a couple of things. One is the kind of error correcting code we're using. Another thing is how much redundancy we have and how much of the message it was received was damaged or has errors in it. And so if the errors get too severe, there could be no way to reconstruct that. Now, let's look at a quick example. We mentioned earlier in an earlier class that English is a redundant language. All written and spoken languages are. And so you'll notice that here's this kind of list of these messages where parts of it have been destroyed. And you notice if you just started with that top one, this top one here, you might have a very difficult time reconstructing what that was supposed to say. But as we move down and there's fewer errors in it, probably when you get down to this third one, then you could figure out what that says without having the extra data or the error data provided. So you could figure out, and part of that is by context. So this is not really an error correcting code. This is just sort of a redundancy built into English that, for example, T with a space and an E, you can probably pretty well guess that that's the. And once you get the idea of what this quote is saying, Carpe diem, seize the day, boys, make your lives extraordinary. Notice we could reconstruct that and fill that in and have pretty good confidence that this is what the message actually was. Now, one thing to note there, if the error rate is too high, the redundancy isn't enough to allow for correction. So in other words, if we wiped out all of the characters in this and just had all of this blank, there'd be no way to reconstruct what that message said. Now, this is not an error correcting code. There's some redundancy built into English, but it kind of relies on the processing power in our heads to kind of look at the context, look at our past experiences with language, and we can still reconstruct that. So even if I'm talking and I leave out, you figure out, so I left out words there, and you could probably say that that you could still make sense of what I said, even if parts of what I'm saying are missing from the conversation. And you do that all the time in your daily lives, just your brain is doing this kind of statistical, probabilistic computation of what the sounds it's hearing with what the ideas that it expects, and it's coming up with this message. And that's why spoken language and written languages have redundancy in them, as it makes it easier to ensure that the message gets through, and it can correct it if parts of it get distorted or missed. All right. Now, one of the things to notice is that with many errors, again, correction can be difficult or impossible. So there's that top sentence there. With fewer errors, correction becomes possible. So you can see now that's to infinity and beyond. We can tell that without even having those extra things filled in. Now, a higher level of redundancy allows for correction of messages with higher error rates. So in other words, the more redundancy we have, the easier it becomes to reconstruct the missing parts of that, or the more missing parts there can be, and we can still reconstruct it. All right, so we've actually seen some forward error correcting codes before. You remember a while back we talked about error detection. We talked about using kind of this redundancy of repetition. In other words, or repetition codes. In other words, if I send hello, and I noticed I messed up my slide there that there should be 3 extra L's here instead of, or we got 3 instead of 6. You can see that there. I'll fix that. But you'll notice that in that saying of hello, if we say each letter 3 times, then we can look at that, and every time I see a block of 3, that I can do that. But I noticed that we said when we went through that if you had one of those missing out of the 3, as long as we had 2 of the 3 were okay, we could always reconstruct what was missing from that in some way. And in fact, you could do that at a bit level too. You could say as long as 2 of the 3 bits of any one position in that match, then we're going to say that we're going to have them vote. For example, if I'm in the first position of this, capital H, I have a 0. So I have 0, 1, 0. I go with 0. If the next position of the H, these 3 H's, I have a 1, then I would say 1, 1, 0. I go with 1. So in other words, we vote on these at the bit level rather than the entire message level, the entire byte level, and we could actually reconstruct some missing bits out of this relatively easily. Now, another one we saw was block parity, where you have that. Remember, you have that kind of horizontal parity that's typical, where summarizing either an even number or an odd number of bits. In this, you do the same thing on some block vertically rather than horizontally. And if there's any single bit that's changed, we can tell what row and what column it was on, and we can flip it back. We can fix that. And one thing to note is that ARQ and FEC, in other words, automatic repeat request and forward error correction, those aren't necessarily mutually exclusive. You can use those together. In other words, you could fix, well, let's look at that. A hybrid system would use both together. And what you can do is you can use forward error correction to fix as many errors as you can. But if the message becomes too damaged, then you could re-request it. So that gives you this ability to say, most of the data that comes through, I'm just going to fix it as I get minor errors. But if there's some major error and the whole thing gets destroyed, then maybe I invest in the the latency, the extra time to re-request that missing data or the missing packet. Now, that does not work in a simplex communication system, obviously, but it can be a way to reduce back and forth traffic in a noisy environment that still has a duplex connection. So that hybrid approach has benefits of reducing duplex traffic while still preserving kind of the integrity of the entire stream if necessary. All right, so let's look at a couple types of forward error corrected code. So the first one are called block codes, and what those do is you have a block of data. In other words, you have some fixed size block. Let's say it's, for our purposes, 32 bytes. And that 32-byte block of code, you basically come up with redundancy on that one fixed size. You send the redundant block either embedded with the code or as a separate block after the code. And then once you've received that, then you decode that. You look at the fixed block size. You say, okay, I can fix this. So in other words, it's always fixed size blocks. Examples of that are Reed-Solomon coding, which is CDs, DVDs, GOLE, low-density parity checks, or LDPC, multi-dimensional parity like block parity that we already saw, and Hamming codes are all examples of block codes. And block codes are used a lot in packet-based systems or where you have this ability to have these fixed-size blocks of data. Convolution codes are the second type of forward error correcting code, and those work on a stream of data or arbitrary lengths of data. And Viterbi is one that's used in most of the spacecraft, Mars rovers, Spirit, Opportunity, Voyager, Viking. A lot of those spacecraft used that kind of convolution code. And the advantage, also there's something called turbo codes that are used in kind of mobile network communication. But those work on a stream of data or an arbitrary length of data. In other words, they don't require this kind of fixed block size that the block codes do. So you can embed the forward error correcting code with the stream of constant data rather than on blocks of arbitrary sizes. All right, now we're going to look at one type of error correcting code today. And the type we're going to look at is called a Hamming code. And what a Hamming code is basically a pretty easy to understand forward error correcting code. Some of the other ones are a little more complex, like if we go back to Reed-Solomon here. So this Reed-Solomon code is a little more complex, but really, really powerful. But we're going to look at one that's easy to understand, easy to get our minds around right now, and that's going to be Hamming codes. All right, now what a Hamming code is first off, very simple to implement, easy to understand, easy to implement, and it can correct all single-bit errors in some fixed size block. It can detect all 2-bit errors. In other words, that if you have this block of a certain size, it can detect if there's multiple bits that are in error, it can detect those. But if there's a single bit that's in error, it can fix it. And it uses a fixed size block of bits. In other words, we're always going to say, here's the number of bits. It's going to be the same every time for that block. We add the redundancy to it. And the central idea behind this is really pretty simple. It's something that we've seen parity before. And if you remember what parity is, just as a quick reminder, parity is adding a bit as either a 1 or a 0 to enforce kind of a rule. So in even parity, we add a bit to make sure the number of ones is even. If it's odd parity, we add a bit as a 1 or a 0 to make sure the number of bits is odd. So the idea there is that we're going to do that same thing, but we're going to overlap those so different parity bits cover different parts of the message. So all of the bits that are powers of 2 in our bit positions for our block are going to be parity bits. All the other bits that aren't powers of 2 we're going to use as data bits. So let's take a look at kind of how that would be laid out. So Hamming code with 4 parity bits. That means that the parity bits with 4 of them are going to be in position. The first position for parity bit 1. Parity bit 2 is the second one since that's a power of 2. And then the next one, if we double that, it gets us to the 4th position. That's parity bit. We're going to call it P4. It's the 3rd parity bit though. And then we're going to have the 8th bit position, which I'm going to call P8, but that's really the 4th one. So 1, 2, 3, 4 total. But I've named them based on their bit position rather than, or on their power of 2 rather than their bit position to make it easier to understand what we're talking about. But all of the other bit positions, in other words, if we look at that's 1, that's 2, 3 is going to be data, and then 4 is parity, and then 5 and 6 and 7 are data, and then 8 is parity, and then 9, 10, 11, 12, 13, 14, 15 are data. All right, so let's take a look at the layout of that. So the layout of that looks like this. So in other words, here are the bits, and I started with 1 rather than 0 on the indexing here. So you can see there's a total of 15 bits here, starting with 1, using the kind of natural numbers rather than place value of 0. So parity, and then bit 3 is data because it's not a power of 2, and then 4 is parity, and then now data, and then back to parity, and then the rest of these all the way up to bit 15, which is data 11, are all data. So in other words, the way that we overlap these works as this. So each parity bit is going to kind of cover its position. So its position becomes part of the parity message. But then what it's going to do, it's going to do every other one after that. So in other words, P1 says parity, skip, parity, skip, parity, skip, parity, skip. And it does that all the way through the entire message, all the way up to the last one. Now parity bit 2, if you look at that, it starts with its bit position, but it's doing it in groups of 2. So in other words, parity, skip, skip, parity, skip, skip, and so forth all the way to the end where we have that data bit 11. And then parity bit 4, again, covers its position, and now we're in groups of 4 though. And you'll notice the groupings of these match the parity power of 2 that these are. So P4 goes in groups of 4. So check 4, skip 4, check 4, and then parity bit 8 covers itself and the remaining data that are in here. So in other words, that's a block of 8 total, 1, 2, 3, 4, 5, 6, 7, 8. So what that does is if you look at any one of those data bits that are in that message, you'll notice that there are at least 2 parity bits covering it. So D1 has those 2 there, P1 and P2. D2 has P1 and P4. D3 has 2 and 4. D5 has 1 and 8. D6 has 2 and 8, and then 1, 2, and 8, and and 4 and 8, and then 1, 4 and 8, and then 2, 4 and 8, and then all of them on the last one. So you notice that what that gives us is this kind of each data bit has a unique covering of those parity bits. So if I can tell which parity bit comes up wrong, or which group of 2 of them come wrong. So in other words, if 1 and 2 show up as being incorrect, and only 1 and 2 show up as incorrect, then I can tell that it has to be data bit 1 that is the problem. Now, that unique coverage is really important here, because what it does is it allows us to correct any single bit error. So in other words, that for single bit errors, because we have that unique coverage of those parity bits in that fixed size block, then we can correct any error. So the idea is the sum of the parity bits that are in error indicate the bit that is in error. Now that's a really clever thing to think about, that we don't even really have to reason through or perform any kind of elaborate logic. We can just say, all right, parity bit 1 and parity bit 2 are the ones that are showing an error. So if we take 1 and 2, let's go back and look at that really quickly. So looking at, here's parity bit 1. So if it comes up, notice that's covered by 1 and 2. So if 1 and 2 are in error, then 1 plus 2 gives us 3. So bit position 3 is the one that's in error. So it has to be data 1 that's in error. Also notice that that works on any of these. So in other words, if all 4 of these show up as being in error, then we add them up, 1 plus 2 plus 4 plus 8. That takes us all the way down here to 15. That's data bit 11 that's going to be the one that's in error. And so this is really clever thing that we don't even really have to do much except sum up the powers of 2 for each of the parity bits, and that will tell us immediately which spot of the bit is flipped to the wrong value, and we can fix that. Now, if a single parity bit is an error, then that parity bit is the error, and that's also really clever. So in other words, that also works out that the sum there. So let's go back and look at that again. So if we show up with just one error, notice P1, each parity bit only is covered by itself. So if everything else looks fine, and the only error shows up is in that parity bit position, in other words, if P1 is the only thing that shows up as being wrong, then we know that it had been corrupted and we can fix it. So the parity bits themselves are covered by the parity calculation, and we can tell if they are the problem or not. All right, so if a single bit is an error, then that parity bit is there. So we can fix the parity bits when they go wrong. We can fix any single data bit when it goes wrong, and it becomes very easy to fix those things on the fly. Now, the Hamming codes, notice that there was no reason for us to necessarily stop. Let me go back one more time here. There's no reason for us to stop at parity bit 8. We could have P16, which would be in the next position. We could continue this for a larger and larger block size. And in Hamming code terminology, the way that this kind of gets described as, you notice we have that Hamming 7, 4 in parentheses after that. That is the typical way of describing these codes. So in other words, the one that we just did was Hamming 1511 because we used 4 parity bits. In other words, what this is the total number of bits. This is the number of data bits. So in other words, Hamming 7.4 has 7 total bits, 4 of which are data. Hamming 1511 has 15 total data bits, 11 of which are data, and so forth. We're meaning the remaining ones are parity. So 7 minus 4 is 3 parity bits. 15 minus 11 is 4 parity bits. And notice we can kind of increase that. And notice that the amount of redundancy, the amount of additional bits needed kind of goes down as we increase this. So when we get up to 6 parity bits, so just one more than that, we have kind of more than double the number of total bits, about double the number of data bits that we get. So we get 57 bits, only 6 of which are parity when we get to the larger thing. We can continue that up to 7 or 8 or 9 or 10 parity bits, and we'll get this larger and larger block size. The problem, though, with getting to, you might think, well, why don't we just make it really large block size? The problem there is that, remember that Hamming codes can only detect a single or only correct a single bit worth of error. And so the larger the block size, if you have a higher error rate, then the more likely it is you're going to have something that is going to have more than one error in it, which cannot be corrected. So Hamming works great for things that have low likelihood of errors, as long as we keep the block size small enough that they can be fixed. And Hamming codes are used quite a bit, but there are other types of forward error correcting code that are worth looking at. Now, one other thing before we kind of move on away from this. All of them, though, no matter what type of forward error correcting code we're using, it's based on some sort of overlapping redundancy. And there's a typo there that should say reconstructing missing portions of the message. But I'll fix that later. So since the errors, one of the problems though is that since errors often happen in bursts, then sometimes you'll see error correcting code systems use this technique called interleaving to spread parts of the message around. So in other words, rather than having a sentence that's all continuous, since an error could happen in a burst, we would want to make it so that it would be better if the error was spread out a little bit at a time in different spots. And there's a technique that's called interleaving that's used to do that. Wireless systems do this all the time, this kind of interleaving technique. For example, wireless systems for things like video game controllers transmit a packet, and they do this interleaving technique before they send it, along with an error correcting code. So if there's some noise that interferes with parts of it, we can still fix it, even if it's a burst error that overlaps like a significant portion of the message. So let's look at the interleaving concept quickly here. So again, back to that message hello, encoded with redundancy. I'm not going to use one of the more complex techniques. I just want this to be conceptual. So here's this message hello. And so what we do is we add our redundancy, and in this case in the form of repeating the H's. There's the E, there's all the L's, there's the O. Now, with a 4-character burst error, 4-character long burst error, it would wipe out all of this entire part of this message. So that's 4 characters, but it went over all of the E's and one of those L's. And note that the damaged H can be recovered because we have 2 out of the 3. But now the E's, those are all gone. I can't like make up data from nothing. I have to have some sort of redundancy there. So the E in this case could not be resolved because the burst error wiped out just the entire portion of that message, including the redundancy associated with it. But if we had used interleaving for that, notice here it is encoded with a redundancy again, same message. But now interleaved, let's say we skip and jumble the message around, so we do every kind of 4th character. So H, 1, 2, 3, E, 1, 2, 3. So it's essentially every count 1, skip 2, count 1, skip 2. And we get to the end, we go back and do the same thing. And that has the effect in this case of now having the message repeated spread out. So rather than all the H's bunched up together, they're kind of spread out and separated in different parts of the message. So now we have that same 4-character burst error in the same spot. So the first 2 characters are fine, but now we get a block of 4 that are wiped out. Again, same part of the message, same amount of lost message. But now when we de-interleave that, we do the opposite of what we did to interleave it, and we put it back so all the H's were okay. The E, all 3 E's were okay, so you can see those there. And now we get to the L, we have basically an L missing, another L missing, no missing. But now when we go through that process of doing our redundancy check, our forward error correcting code, you'll notice that the H's, that votes is okay, the E's are okay, L is okay, L is okay, O is okay, exclamation mark. So now we can reconstruct that message just fine. And we really had the same amount of error. We had the same methodology for doing our error correcting code. The only difference here is the interleaving, where we took the message and put the contiguous parts of it in different spaces so that a burst error did not necessarily get rid of all of the data. Now, interleaving is used a lot in wireless communication systems on a packet because of that kind of nature. of spreading the message out so that the different parts that would be next to each other are now spread out in the message, so a burst error cannot get the entire thing. All right, other types of forward error correcting code that are really important, and we're not going to go into the details of these right now, but Reed-Solomon codes, again, we said those are used in CDs, Blu-ray, QR codes, spacecraft. Really, all of those spacecraft use that, and the reason they use that is because it's a really effective code. It's a really useful code, and the reason it's so useful, let's look at the properties of that. If you add a number of symbols of check data to a block, and let's say we're adding T symbols, so T might be, I don't know, like 50 or 100 or 1,000 or whatever it is. It depends on the block size and how much errors we want to be able to correct and detect. So if we add T symbols to a check data to block, we can detect up to T error symbols. In other words, let's say we have a block of 1,000 symbols. We add 200. Let's just add 100. We add 100 errors or 100 check data symbols. Then that means we can detect up to 100 cases where 100 of those 1,000 symbols go wrong. And then we can correct up to T over 2 of those. We could correct up to 50 of them being damaged or destroyed. And that kind of property of Reed-Solomon codes is really important because it allows us to tune the amount of error correction and error detection to the block of data and the error rate that we see in practice, which makes it a really useful methodology, because if we want to be able to correct more errors, we just add more symbol to our check data block. If we have a very low error rate, we don't want to use the bandwidth on that as much, we don't need to, then we can lower that down to some extent. Now, you might want to look into that a little bit. That's Reed-Solomon codes are a really powerful thing. We don't really have the time in this class to go into that. And really, we could have an entire semester class in error correcting code systems. There's a whole bunch of these. They're all mathematically based. They're very powerful. Some of them have filtered to the top, just like CRC is used everywhere because it's a really useful technique. Reed-Solomon codes are used all over the place because it's a really useful technique. But the concept of it is not too dissimilar to the Hamming codes. Remember, Hamming codes are kind of easy to understand, but the central concept is overlapping the redundancy in a way that allows us to reconstruct the things that are wrong. Reed-Solomon codes do the same thing, but the mathematical process for doing that is a little more complex than just simple parity that we had in Hamming codes. And I would suggest taking a quick look at maybe the Wikipedia entry for your Reed-Solomon codes. It's a really fascinating thing. So if you're ever developing a system that you really cannot afford to have a back channel and you want to have a really robust way of doing an error correcting code, I would suggest looking at Reed-Solomon codes. Now, we're not going to cover any of those other methods in great detail. I want to just mostly in this class get you kind of conceptually aligned. Make sure you understand kind of error correcting code in that it's using redundancy. It's using redundancy in kind of this overlapping way that gives us the ability to not just tell when something went wrong, but to fix it. I'd also make sure to understand Hamming codes and how those work. Those might show up on the quiz or exam later on. But the error correcting codes, really powerful, really useful, really cool. I'd suggest investigate on your own a little bit. And that's really all we're going to do for today's class. Next class, we're going to dig into a topic called information transfer, which is related to error detection and error correction. But what we're going to do when we move into that next class is we're going to look at how do we get a large amount of data moved across the system. And then we're very quickly going to move into actual network programming. We're going to write code that talks over the internet. And we're going to use some of these concepts in order to do that. All right, so that's it for today. Stay safe, wash your hands, do not go outside and interact with other people if you can avoid it. It's kind of strange times that we're in right now, but everybody stay safe and be sure to ask any questions you have. Text me, email me, or ask them on the comments section of this video, and I'll be happy to answer them. All right, thanks.